All right, guys, this video is on EOC review notes, units 4 through 5. Okay, starting with exponentials. So exponentials are always raised to the power of x. The variable is your power. Okay, the shape is creating a curve. Now the direction of that curve is depending on the value of a. Keep in mind that in standard form, y equals a times b to the power of x. Now what's nice is you have a reminder of this on the EOC formula sheet, so feel free to click that formula sheet and reference that while you work on the EOC. Okay, if a is positive, okay, then it faces up. So your exponential curve is going to look like this. If a is negative, okay, then it faces down because there was a reflection over the x-axis when that negative happens. Okay, now deciding whether it is growth or decay, that has to do with the base value, okay, not the leading coefficient. So if b is greater than 1, then it is growth. Examples of growth: y equals 2 to the power of x, or y equals 10 to the power of x, right? Those are examples of growth. But if your base is less than 1, then it's decay. So y equals 1/2 raised to the power of x, or y equals 2/3 raised to the power of x. That would be decay. Right? Then we can talk about all the different transformations that are associated with this. Okay, transformations tell where the origin or where the graph was moved in relation to the origin. Okay, the most basic parent function that you can have, right, is just b to the power of x. Anything you do on top of that is going to cause a transformation to occur. Okay, the k value, if k is positive, it's causing it to shift up or down. So up or down for that k value. Okay, the h value is going to cause it to go left or right. But this one's a little bit counterintuitive. When you're subtracting, you're going right. When you're adding, you're actually moving it left. Okay, and then the base, right? The base, we already talked about what that causes, whether it's growth or decay. And the a has to do with whether it is being stretched, shrunk, or even reflected over the x-axis. So if a is greater than 1, then it's being stretched. If a is in between 0 and 1, then it's causing a shrink to occur. Okay, in the next section, we're going to talk about characteristics of exponentials. Okay, we can talk about domain. Domain is all of the x values. We'll notice we'll draw arrows on here just to indicate that that's going on forever in both directions. So it's slowly getting wider and wider and wider. So we're going to use every x value from negative infinity all the way to positive infinity. But the range is always going to be limited based on the asymptote. So this always is based on location of asymptote. Notice that in this case, the asymptote is right here. It's approaching the asymptote, but it's never crossing it. So we will not use the value 0, but we'll use everything above it. So from 0 all the way to positive infinity. All right, the asymptote is always going to be y equals a number, right? That's a horizontal line. So in this case, it's y equals 0. The x-intercept, well, it's approaching the x-axis, but it's never actually going to touch it. So there are none in this case. The y-intercept is at 0, 1. If you read the graph from left to right, that is a decreasing function. In behavior, what's happening on the right and the left side? Well, as x goes to positive infinity, that's the right side of the graph. As x goes to negative infinity, that's the left side of the graph. Okay, on the right side of the graph, what y value is it approaching? Right, f of x is a fancy notation for y. Well, if you look at the y-axis, right, if on the right side of the graph, we're approaching a y value of 0. On the left side of the graph, we're approaching a y value going all the way up to infinity. All right, last but not least, we're going to find the rate of change from x1, okay, equals -2 all the way to x2 equals 1. So essentially, we are finding the slope from here, x is -2, to x is 1 here. So what are those coordinates? Let's write them down. That's -2, 4 and 1, 1/2 or 0.5. Well, to find rate of change, that's essentially finding the slope that goes in between those two lines. So we're going to do y minus y. So 4 minus 1/2 over -2 minus 1. So I have -3.5 on top, and I have -3 on bottom. I apologize, sorry, that's positive 3.5 on top and -3 on bottom. When you punch that into your calculator, you're going to get -7.6 as your rate of change between those two locations. Remember, the rate of change formula is on the formula sheet if you need to reference it on test day. Rate of change, right, that's the slope in between 2 points. Right now we can talk about geometric sequences. Okay, with geometric sequences, you are going to be looking for the common ratio. Or R. Okay, remember, when a sequence is geometric, it's because you're multiplying or dividing by the same number again and again and again. Okay, the formula for this is on the formula sheet. So let's see. Geometric sequences. The two formulas are right here to reference. Okay, the explicit formula is a sub n equals my first term times r to the n minus 1. For the recursive formula, it's a sub n equals r times a sub n minus 1. You have to include the first term whenever you're talking about the recursive formula. All right, so here's an example. Given this sequence, well, let's see, what are we doing each time? Looks like it's times 1/2, times 1/2, times 1/2. So what's the common ratio? Well, you're multiplying by 1/2 every time, so that is my common ratio. And then let's write the explicit formula. A sub n equals my first term, which is 40, times 1/2 to the n minus 1. So common ratio and explicit formula. Next, we're going to talk about the growth and decay formulas. Okay, growth is going to be y equals p, your principal, times 1 plus r to the power of t, where decay would be y equals p1 minus r to the power of t. Okay, the 1 plus r is the growth factor, and the r is the growth rate. Same thing, 1 minus r is the decay factor, and r is the decay rate. Now, these formulas are very similar to the compound interest formula. Now, the compound interest formula is also on the formula sheet. The only difference is these have an n and this one does not. So if you see the word compounded, that's because you're going to have a value for n, for how often it is compounded. If it is just growth or decay without their compounding, okay, interest, then your n is 1, which turns it into these formulas. So Keep in mind, okay, the number of times that it's compounded, okay, will determine your end value. So if it's compounded monthly, compounded daily, compounded quarterly, compounded semi-annually, that will change your end value. Okay, P is the principal amount or the original amount. R is the interest rate in decimal form. N is the number of times the money is compounded in a year. Which is why if it's just compounded yearly, right, then it turns into those formulas. T is the number of time in years. All right, so essentially you would be given the principal amount, the interest rate, the number of times it's compounding, and the calculation for how many years you want to see into the situation, for how much money you have, okay? All of it would just be plugged in and then calculated, which you'll see in your practice problems that are on the next page. Good luck.